So this is work in progress, and so hopefully it will generate some discussion. And it's about trying to understand why the Atlantic is saltier than the Pacific. And on the first slide here, okay, let me get the little arrow here. I have the various proposed reasons that are in the literature of why the Atlantic is saltier than the Pacific. And the first two, I think, have been discussed many times, and involve the AMOC and the Atlantic meridional overturning circulation. The idea is that because the AMOC transports heat northward, it makes the North Atlantic warmer than the North Pacific, and that increases evaporation. In addition to doing that, the Atlantic meridional overturning circulation carries the salt from the tropics into the subpolar region. And so these are pretty much oceanographic reasons. Well, actually, the first one is really an oceanographic reason mediated by the atmosphere, which being warmer increases evaporation. And then these second two are really atmospheric reasons. And so the idea is that the structure of the orography along the western side of the American continent, that is the eastern side of the Pacific, is such as to block precipitation preferentially in the Pacific. A more recent idea is that just because the Pacific is so much wider than the Atlantic, the footprint of precipitation that occurs preferentially in the Pacific rather than the Atlantic. In other words, some of the water that evaporates in the Atlantic that then gets carried towards the Pacific and precipitated there, and that is not true of the water evaporated in the Pacific. Then there's an old theory about the fact that there's more enclosed sea in the Atlantic, in particular the Mediterranean, that is highly evaporative, although I would say this suggestion has been somewhat disputed more recently. Then another reason that's been put forward is the fact that the low latitude of South Africa relative to the higher latitude of South America favors transport of high salinity water from the Indo-Pacific to the Atlantic rather than into the Pacific. And then finally, another hypothesis that's been put forward is that the Pacific has larger wind-driven circulation, which has a larger wind-driven, directly wind-driven heat transport, and so there's no need for a meridional overturning circulation to transport heat in the Pacific, and that also, given the reasons that were here considered here, that salinifies the Atlantic preferentially. So, so many processes that are listed here involve the meridional overturning circulation. Then one might ask the question, okay, so then why is there no Pacific meridional overturning circulation, or PMOC? And so, we have to consider that the present overturning circulation is actually a global circulation. And so you have water that, well, where shall we start? Let's start from the North Atlantic, that sinks in the North Atlantic, then comes down the Atlantic, then enters the circumpolar currents, and from there it enters all the other basins, that is the Indo-Pacific, and then it returns to the Atlantic, making the whole global tour of the whole world. And so the way to think about it is that the overturning is that, yes, it is a global overturning, and what is special about the Atlantic is that there is sinking in high latitudes in the northern hemisphere, whereas there's upwelling pretty much everywhere else in the ocean. But one could imagine a situation where there would be sinking in the Pacific, and the return flow would be in the Atlantic. That's what I mean by the PMOC. So, so to try and get at this problem in the simplest possible, well, possibly not the simplest, but in one simple context, is to look at a very simplified geometry of the world ocean, where you just have two basins. In this case, they don't even occupy the whole world, that have the same latitudinal extent, and they are just divided by continents. Here, they are just one, very thin edge. Ocean only, I should say. We don't consider either atmospheric processes nor coupled processes. And the only difference between these basins is that one is this one, which we'll call, in the Pacific, is twice as wide as the other. And then they're connected by a circumpolar region. And other than that, there's no other asymmetry because they are forced by wind stress, relaxed to surface temperature, and have prescribed freshwater flux here, which are independent of longitude. So they're just the same for both basins. And then we started by looking at this in low resolution, shows just 1 degree grid. Then eddies are parameterized using GM. Linear equation of state. Vertical diffusivity quite small, 210 to the minus 5, plus a mixed layer. And the bottom is flat, except there is one ridge here. So that, because there is only one ridge here, you might say that is a slight asymmetry between the two basins. But we have also tried putting a ridge here and a ridge here in the channel, and it makes no difference at all. So what happens with this symmetric with longitude forcing? Okay, how do I go next? Sorry. So here is the residual overturning circulation. So that's the overturning circulation calculated in buoyancy rather than z coordinates, but then remapped as a function of depth and latitude. And what I show here are, in the top is the narrow basin, and in the bottom is the wide basin. And let's concentrate on these figures on the left first. What is shown as color is the residual overturning circulation in the narrow basin. As you see, there is sinking there in high latitude, while in the wide basin, there really is no overturning circulation to speak of. There is a little bit of a overturning in this sense. There's kind of accompanying this branch. And the little lines here, the black lines, are buoyancy surfaces, zonal average buoyancy surface. And there's one buoyancy surface that is highlighted, this dark, thick black line, which divides the upper branch of the overturning from the lower branch of the overturning. Now, this is what you obtain regardless of the initial condition if the forcing is zonally symmetric. However, we wanted to see whether maybe there was a possibility of obtaining a PMOC, and so we made, the forcing in the freshwater flux asymmetric by making it less fresh in the Pacific, that's that red dashed line, and a little bit saltier everywhere else. So if you impose an asymmetric freshwater forcing rather than symmetric, then you can't, and it has to be of a certain threshold, that asymmetry, otherwise it doesn't happen. Then you can get a Pacific meridional overturning circulation, which is plotted here. Okay, and again, this buoyancy surface divides the upper branch from the lower branch because I'll need it later. Now, however, once you're in this state with Pacific meridional overturning, and as you see then in the narrow basin, it looks like the Pacific sort of in the other case, right? These are kind of reversed. If you very slowly put the freshwater flux forcing back to the symmetric case, so you remove this asymmetry, then this circulation reverts to the narrow basin sinking. And no matter how slowly you do it, we did this over the course of 20,000 years, and in 500 to 1,000 years, it reverts to the narrow sinking when the forcing is symmetrized again. So there definitely seems to be a preference for sinking in the narrow basin, and the only reason is because it's narrower. So to look at this a little bit further, we plot the salinity here, zonally averaged and integrated over that upper branch of the overturning defined by that buoyancy surface. Okay, so integrate the salinity vertically above that buoyancy surface and then zonally. And here it's where it is. And there are four curves because there are two states and two basins. So the solid lines refer to when there is sinking in the narrow basin, so that it's like the AMOC situation. And as you see, so the sinking basin is in red, and the non-sinking basin is in blue. So for the solid lines, you have that the narrow basin is in the high latitudes of is saltier than the non-sinking basin. This is also true when you have wide basin sinking. The wide basin, that's the dashed red line, is saltier than the blue dashed line, which is the narrow basin, which is not sinking in this situation. However, the difference in salinity when you have wide sinking is less than the difference in salinity when you have narrow sinking, despite the fact that to obtain this wide basin sinking, we put more salt at the surface in the wide basin, and yet the salinity difference is less. Is that clear? I can't hear you, so I don't know. So even though there's more salt put in the wide basin, there's less difference here than when you have narrow basin sinking and the forcing is symmetric. So the hypothesis is that the reason why the wide basin sinking is unstable when you have symmetric forcing is that in fact there's more salinity in the narrow basin. So how to prove this? Well, we don't have, one of these code where you can find unstable steady state. So the best thing that we could do with a time-stepping code was to advect a tracer with the same velocity field as the primitive equations, but instead of being forced by the asymmetric freshwater flux, is forced by a symmetric freshwater flux. So obviously when we have narrow basin sinking, then the tracer and the salinity are identical because they're advected by the same field of velocity and they have the same freshwater flux. So the solid lines in this figure and this figure are identical. Now for the wide basin sinking instead, there's a difference because we use the same advection that is in this primitive equation calculation, but the freshwater flux is symmetric. And in fact, what you see happens, so you should compare the two dashed lines here with the two dashed lines here, and you see that in the high latitudes, in fact, the freshwater flux, the salinity, well, it's not salinity, the tracer is higher in the narrow basin, which is not sinking, than in the wide basin. So it appears that even when you have an advection field such that the wide basin is sinking, the salinity is higher in the high latitude of the narrow basin, even though there's no sinking going on there. Okay? So that seems to be what is happening here. So let me show you what the flow field looks like. Now this is a three-dimensional field, so it's not so easy to visualize. So the one thing that we have visualized with it, I think it's perhaps useful, is to take some kind of pseudo streamlines of the flow integrated vertically above the buoyancy surface that divides the upper branch from the lower branch. So this is kind of these are streamlines of the upper flow of the meridional overturning circulation. It is actually a divergent field, so it's not a true streamline. That's why you see lines going into the wall. But don't worry about that. It's okay. So this is how mathematically how it's derived. You integrate to the zonal transport and you add the diapycnal component. That's why it's actually divergent. And so here is what happens when you have sinking in the narrow basin. So the northern hemisphere is kind of isolated. This is the wide basin, and so let's not even talk about that. But what happens is you have this circulation here in the wide basin that transfers into the narrow basin, and then it sinks. Okay, so this kind of visualizes the exchange between the two basins. Similarly, when you have wide base sinking, the northern hemisphere is isolated. So let's just look at the southern hemisphere. You have these streamlines here, and they go into the wide basin, and then here's periodic, so I have to come back. And then it snakes through and then sinks in the wide basin. Now, what is interesting, and I don't have time to show you this, is that I should have pointed that before. So let me go back. Oops, there it is. If you actually look at the magnitude of overturning circulation in these two states, it's about 15 spheroids for both. So even though this basin is twice as wide, even though you have sinking in a basin which is twice as wide in this case than in this case, the zonally integrated transport is about the same. It's not twice as much. And that's because the upwelling is always the same. The upwelling is made of the Ekman transport, upwelling in the southern hemisphere, then the upwelling due to diapycnal mixing, and that's about the same no matter where you sink. So that's why the strength overturning is the same regardless of sinking. That has important consequences because that means, sorry, I have to go forward. That means that even though because the transport in this is the same for narrow sinking here or wide sinking here, the velocity, which is the transport per unit width, is actually lower in this case. And what that does, and let me skip a slide here because I'm running over time, otherwise I'll run over time. And what that implies is that if you consider the combination of transport in the upper part, in the upper branch of the overturning. In a case of narrow sinking, and I'm showing here only the northern hemisphere, or in a case of wide sinking, and again I'm showing only the northern hemisphere. And that is comprised of now gyres plus this flow through, of constant transport. In both cases it's 15 spheroids. Then there is a very different partition in the two cases between the flow that kind of goes through and the flow that is recirculated, because the gyres are obviously wider, wider and stronger for the same wind stress when you have a wide basin. That's just a consequence of spheroidopilation. And so if you think about what happens when you have an advection flow like this, which is a mixture of flow that goes through and flow that is recirculating. When you specify the flux at the surface, then the flux gets, the salt in this case gets accumulated in these closed streamline regions and then diffused inefficiently through the open streamlines that then efficiently carried through. Now this accumulation of salt, salinity, in the subpolar gyre is much less prominent in the Atlantic than it is in the Pacific. So number one. And number two, if you actually evaluate the Peckley number, which is a measure of how efficient this flow is relative to the diffusion, you find out that it scales like 1 over the width of the basin. So the Peckley number is much larger, in fact much, it's by a factor of 2 larger in the narrow basin than it is in the wide basin. So there are 2 things going on that prefer a narrow basin, prefer accumulation of salinity in a narrow basin versus a wide basin. 1, there is less storage or accumulation of freshwater flux by the gyres. And 2, there is more efficient transport from the subtropical gyre, which is where the salt is put in, towards the subpolar gyre. So to test this hypothesis, we just do, a very simple problem where we advect a tracer, which is forced just like the salinity, in 2 dimensions. So we assume that the tracer is vertically homogeneous, and we are thinking about the upper branch of the AMOC, with a 2-dimensional flow field, which is shown here, which is a mixture of gyres plus a through flow. And I don't know if you can see the through flow, but actually the flow here goes through the boundary, because that's supposed to be the buoyancy surface through which you have sinking or not sinking. So here's when you have sinking in the narrow basin, and here's where you have sinking in the wide basin. So here is sinking, and as you see, there's much more gyre closed streamlines in this situation than in this situation. So when you do that with this kind of passive tracer, you don't get exactly the pattern that we get in the primitive equation, but you do get a hint that the difference in salinity when you have narrow basis sinking, which is the solid lines. This is where this is the narrow basin which is sinking, and this is the salinity in the wide basin which is non-sinking. And the difference in salinity is much larger than when you have sinking in the wide basin. You see here there's a difference in salinity between the narrow sinking basin and the wide non-sinking basin, which is larger than the difference in salinity between the wide sinking basin and the narrow sinking basin. So at least part of the reasons are due to this 2-dimensional advection. Of course, there must be others, since the 2 fields don't look the same, and we are looking into perfecting this. So the conclusions are that numerically we have documented that symmetrically forced 2 basins prefer sinking in the narrow basin, and that difference is due to the salinity distribution, and that we believe that the interplay between the residual overturn circulation and the wind-driven gyres is crucial to the salt distribution in the northern hemisphere of both the sinking and non-sinking basin. And I'll stop for questions.
The conference has been unmuted.